Okay, so last time we are here, we completed the assumption part that based upon the assumptions, these OLS estimates which we are trying to derive with the OLS method, with the bivariate case and the multivariate regression analysis by matrix method, have few important properties based upon we generally decide that why we prefer OLS method or why we apply OLS method. So today I'm going to start with those properties. These properties generally we say Gauss-Markov theorem, and the name we generally say blue properties. That's best linear unbiased estimators. So this is the one specific reason that means these particular OLS estimates have these properties. That's why generally we prefer these estimates and we use this OLS method. Unless OLS has these properties, we have problems, and I think we are not going to apply OLS method. But these properties are only proved when assumptions will fulfill. If there might be any problem with the assumptions, then it's not possible to fulfill these properties. And then we have to decide whether we apply OLS method or not. So let's start with the property part. Assumptions we did last time in the last lecture. So these properties are, as we call, Gauss-Markov theorem, best linear unbiased property of these estimates, beta 1 hat, beta 2 hat, or if it's more than one independent variable, then beta 3, beta 4, all these estimates has these properties. Today I'm going to start with the linear and unbiased and the minimum variance that we will do tomorrow or day after tomorrow. Let me see my schedule for tomorrow, because in this week I also have to make this data set out of the Woolrich. So also required 1 or 2 days for that. So first start with the linearity. Now linearity, in generally the linearity meaning is that if you have any particular estimate, let's suppose we have a estimate like mean or any theta hat, if it's a summation of simple terms like not any other form like square, cube, under root, it's a linear sum, constant change, then we see it's a linear parameter. Now we estimated the beta 1 hat and beta 2 hat, or if it's a matrix method, then all the betas. Now we have to see whether these estimates are linear. And second, we try to understand that is there something important about linearity, about the parameter, that in assumption we took that these estimates are, if it's a population, our parameters are linear. But here, after estimating with the derivation of the formula, now in the end we have to see whether they are linear. And second, what's the importance if they are linear? Is there any significance? Means we are saying this is the property of these OLS estimates, but what significance this property is giving us? So first, just start with the slope coefficient, that was our beta 2 hat, or if you are going with the Kortzianis using notation beta 0 hat and beta 1 hat, and Gujarati is using beta 1 hat and beta 2 hat. So name you can give any name, but the meaning is same. This is the slope coefficient that we estimated. This derivation we did with the bivariate method, OLS method. So here we have to see whether this estimate is linear or not. Similarly for the beta 0 hat or beta 1 hat. So this is the derivation that we did with the OLS method in the second, in the, I think second or first lecture of this particular series. So this is the formula for beta 1 hat. Now here you have to see whether this particular component is linear or not. So to understand that, we have to go through this particular values, that what these values will indicate. So here if you can see that let me put it in form of this particular term, means this xi upon summation xi square, whole xi term in a, let's give a name ki, which is equivalent to xi upon summation xi square. This xi, small xi, is in the deviation form. So we are taking here the deviation form. And if you put this ki in this particular value, it is summation ki yi. This is the value of beta 2 hat that we estimated last time. Now here we have this assumption, the OLS we did, as I already told you, that these properties will only fulfill or proved when OLS assumptions will fulfill. So one or the other way means all these properties are depend upon these assumptions. So in this particular case, now we are going to use assumption where we say that x are a set of fixed numbers in samples. Means x is fixed in the repeated sampling. That assumption we did last time. If you have doubt about that assumption, then again go through that particular lecture and study that assumption. Means all these assumptions has role to play to prove these properties. That's the one reason that we are using these properties, and we study these assumptions in detail. So let's suppose this is the value of beta 2 hat. Then if I extend this term, that it is summation ki yi, but it means that if we multiply all individual ki yi, then the summation will give us the value of beta 2 hat. If give you the example with a numerical example if you want. Okay, let me open a new one if it's not opening. Okay, so the last time the derivation of we did for these parameters or estimates is that we estimated with the bivariate method. This is the value of beta 2 hat, beta 1 hat, and this is with the matrix method. So first we are going to prove with the bivariate method that this particular properties of Gauss-Markov theorem, all estimates are blue. So first starting with the linear. So from here that I already proved that this particular value, again now I'm going that this particular beta 1 hat or beta 2 hat, it's a Kortzianis notation, or if you are going with the Gujarati notation, it's beta 2 hat, slope coefficient. In derivation, we did it that in the deviation form, that this particular value is equivalent to this value. And to put it in form of linearity, generally they use this particular term that beta 2 hat is equal to summation ki and yi. Now ki here generally they take as xi upon summation xi square. But actually these values we have, where this small yi is equivalent to y minus y mean. So now if we can go by this particular methods, and you might have doubt that where this y mean will get disappeared, that where this particular value is, and why we are saying that this particular term is equivalent to summation xi yi upon summation xi square. And if we say that this particular value is equivalent to k, that ki is equal to xi upon summation xi square, and we can say that this particular value is ki into yi. So where this particular term, now you have this doubt, might be doubt, that where this mean value is disappeared. So for just let's see where this particular mean value is. If you can break down this particular term in these two terms, then you will get, I am just giving you this, that where this particular value is disappeared. So this particular term I can write as summation xi, then within a bracket y minus y mean summation xi square, which is equivalent to summation xi yi summation xi square minus y mean summation xi upon summation xi square. Now we know that this particular value, that summation of x minus x deviation is equal to 0. So that's why this particular term will disappear. This particular term will disappear. So we can say that this particular term is equivalent to this term, and out of this term we are saying to the x term that it is a summation ki yi, means we are taking this whole term, the x deviation form, in form of ki. So I hope you don't have any doubt now that why we have written that beta 2 hat is equal to summation ki yi. Now how we prove that this is a linear, that linear estimate. Now if you can see that this particular term summation ki yi, what it means is that all individual multiplication, then plus k2 y2 plus k3 y3 plus and so on, kn yn. So what it means in term of numbers, if you have a data of x and y, then first you have to find this xi, that is x minus x mean, means first you have to find summation x by n, that is your x mean. Then you can take deviations, that is your summation xi. And if you have this, now this particular term is equivalent to 0, that we know that if we take a deviation at summation, that's equivalent to 0. So next we have to take x square, this denominator term. Now if you take its summation, that is summation xi square. Now if you individually divide all these values, like xi upon, means this particular value, means for all the samples, we said that these x values are fixed in the repeated sampling. So we are saying is that this particular term is fixed in the repeated sampling. With this particular term, not need of this particular term we are saying fixed in the repeated sampling, and that assumption we took last time in the OLS case, that this x variable is fixed in a repeated sampling. So we are saying this particular term is fixed in repeated sampling. So if this term is fixed out of this, all the values, this k are fixed in the repeated sampling, and what it means is that beta 2 hat will depend upon the y values. That's the dependent variable. I hope you are getting this point, that this beta 1 hat, or if you are going with the Gujarati notation, beta 2 hat is function of y, that is a dependent variable, because we are saying in the repeated sampling this x value is fixed. So it means that this is the summation of this constant summation of these all the ki yi values, and out of that ki is fixed. So it means beta 2 estimate is a function of y, and it's a summation of simple terms without any under root, reciprocal, square. So we can say this is a Linear estimate. The KIs are fixed constants from sample to sample and may be regarded as constant weights assigned to the individual values of y. So beta 2 is a function of y, and that is a summation in the linear form. So we say estimate beta 1 or beta 2 hat is a linear function of the y's and a combination of values of the dependent variable. Here it's actually beta 2 hat, sorry, beta 1 if it's Cotsianis and beta 2 hat if it's Gujarati. So this is for the slope coefficient, that this particular coefficient is linear in estimate, and that's the first property of this Gauss-Markov theorem we have. Similarly, intercept coefficient. Now, here you might have this that from where this particular term is appeared, because if I go to this derivation, we did it that beta 1 hat is equivalent to y mean minus beta 2 hat. And in this derivation, if you go, I have put here intentionally that again we have to prove that this is a function of yi only, other terms are constant. So is it this term, particular term is equivalent to this term? So first just try to understand that how this particular term is equivalent to this particular term. So let's give you this example. This beta 1 or beta 0 hat, if it's a Cotsian notation, is equivalent to y mean minus beta 2 hat x mean, that we did from the derivation. Now put the values here. Y mean is summation y upon n x mean, and beta 2 hat, we prove that this is equivalent to summation ki yi. So just put those values here. Summation ki yi. Now I can take summation out of the bracket. Then within a bracket, it is equivalent to 1 upon n minus x mean ki and yi. So now you can see that this particular term is equivalent to this term. So now to prove linearity, we need this particular term. That's why here you can see that this is equivalent to this term. Any doubt? Yes, I hope you got this point. Because here we're trying to say that these estimates are in formula, actually they are the, this depends upon x and y both. But since in the assumption we have this assumption that x is fixed in the repeated samplings, so then we can say this particular estimates only depend upon the y, and it's again linear combination, because here this x is constant, this x mean, ki depend upon the xi, and xi we are saying that x values are fixed in the repeated sampling. So again this value depends upon the yi, and it's a linear combination of these two multiplications. So we can multiply these two and take a summation, so that will give us the value of this beta 1 hat or beta naught hat, beta 0 hat. So again it's a linear function of the sample values of y. So this both the estimates are a linear function of y, and it proves that these are the linear function of random variables such as the dependent variable y in the regression model. So this is the first property with these all as estimates if assumptions will fulfill. Here only with, although we only took as this assumption of fixed in the repeated sampling, but this assumption is crucial to prove these estimate whether they are linear or not. Now the next next property is it is unbiased and that its average or expected value is equal to the true value. Now here you have to understand this assumption first in a graphical form, that when we have any particular sample in hand, when we work with any particular sample, that sample have only one estimated slope coefficient. But if you have n number of samples, then each sample has its own slope coefficient. And if you take expectation, means average of all those slope coefficients of different samples that are equal to true population estimate parameter. And this property we say unbiasedness, and it's very crucial because since we work with the sample estimate, so we don't know can we rely it for the population estimate, that we don't have any clue about that. But unbiased property proved it that it's not true that actual sample estimate is equal to the population estimate, but at least if we take an average of all the sample estimates, they are equal to the population parameter, and this is we say as a unbiased. So whenever in practically you have a data set, you work on the regression model. At that time, you only have one single value of that slope coefficient or intercept coefficient. Or if it's a multiple regression, then a partial slope coefficients. But at least in theory, it is proved that if you have n number of samples, like you do same regression model on 10 different sample size of 100 each, then definitely you find different slope coefficients for all the samples. And if you take an average of all those 10 samples slope coefficient, that is proved to be equivalent to the population parameter. So in practical way, it's not possible to prove it because there are n number of sample size, right? So you can't take all the sample size and then calculate the average and then see whether it's equal to the population parameter or not. But you can do this exercise, means with the NSS data if you have, then just break down the data in thousand observations, and first on the aggregate data just calculate the one parameter slope coefficient, that's called the all India level. Then again do same exercise by dividing sample size in 1000 or 2000, and then take average of those coefficients and just try to see whether that is equivalent to the all data. More or less, you're going to be that average is equivalent to the all data NSSO data. Similar exercise you can do with the census. If after the series, if I have time, I'll try to do that so that you can understand why we see these are unbiased. But theoretically, we can say that if we have n samples, means it's not some specific quantity that 5, 10, 100, no, n samples, their expected value or the average value is equal to the population parameter. So let's see, is it proved that is it possible to prove it? This property we call as unbiased. Today generally I'm going to prove these properties for the slope coefficient. Then similar is the way to prove this for the intercept coefficient and for other slope coefficients, but the derivations will definitely a few equations and notations will change. So rather than that, I'll do it with the matrix as well, because in matrix method we are not required to do it one by one. In the matrix method, it will automatically derive for all the parameters, all the S sample estimates. And later on, for the intercept coefficients, I'll solve this particular derivation, and I'll put as a 2 or 3 minutes video, so that steps, if you want, you can just see from the YouTube. But today I'm going to show it with the slope coefficient beta 2 hat. So to prove this particular property, first you need to know these basics about the expected values, properties of the expected values. Expected value of constant is always constant, means It's like average of constant is constant. Means if you have a, let's suppose, five number five times, and if you take its average, that's also a five. Means take a summation of five, it's 25, then divide by the five, it's five. So expected value of any constant is constant. Then if you have this particular equational form, then the expectation is only for the variable. Constant will come out of the expectation, and for constant expectation, expected value is same as the value of that constant. So this one or two properties we are going to use in this particular derivation to prove that average of all sample estimates or expected value of all sample estimates is equal to the population parameter. So let's start with the slope coefficient. I hope you now got that what unbiased is mean, that what we are saying, that this is when you have one single sample study, or when you work with the regressions, that time you only have one estimate. It's not about that estimate. It's about the theoretical, that if you have an n sample size, an average of all those slope coefficients or intercept coefficient, whatever coefficient you are trying to prove, is equal to the population parameter. So let's start with the slope coefficient. This derivation we proved with the OLS method for bivariate, that slope coefficient, if you're taking a Gujarati notation, then it's a beta 2 hat. That beta 2 hat is equal to summation xi yi divided by summation xi square. This derivation we proved in the beginning, that this particular value is, I also given a proof to you that this particular equation, these values are equivalent to these values, and we can write it in a deviation form in small xi and yi. So this is the value of this beta 1 hat, or slope coefficient beta 2 hat. Now just break it down. Just put yi values, y minus y mean, then multiply this summation, and here in this particular case, since y's mean is the constant, it come out of the summation that I also explained you in the beginning, these properties of summation. So this is the values for this particular term. Now here it's a summation xi. That's I told you that this is equivalent to 0, because if you take a deviation from the mean, and if you take that summation, that is equal to 0. So now we will remain with this particular term. And here to this particular term, x upon summation xi square, let's say we give it a name ki, because this value x value is fixed in the repeated sampling, so equal weights are there. So just for simplicity, put it as a notation ki, this particular term. So now we have a beta 1 slope coefficient equivalent to summation ki yi. Means many times you might find this difficulty in these derivations. The only way is that do it again and again, because now you have the recorded lectures, so you can just pause it down at any step where you are working, and then go back that how that step is linked with the previous step, and try to understand that. Means at many places we are changing notations, and at many places there are few tricks to prove these derivations, and at many places we are going to use assumptions. So generally in the statistics and the mathematics, when we have to prove anything, we use these tricks, that we do some tricks like summation or changing the notations, or sometimes, and here the crucial part is we are going to use assumptions to prove few steps. Like this is here I'm using that summation xi is equal to 0, that's proved, and intentionally we have segregated this part only. So these are the tricks. It means that in the derivation part we use these tricks. But you have to understand this process, that it's not that you remember all these steps. The important thing is that you at least you remember that why these properties and what's the significance of these properties for your estimates for your regression model. That's the purpose here. But at many bachelor and master courses, students also try to prove it. For that purpose only, I am also giving the derivational proofs to you, so that any one of them is watching it, he or she might get use these derivations if he or she stuck at any particular step. So our coefficient now, slope coefficient is equal to summation ki and capital Yi. Now this particular mean term is disappeared because this summation xi is 0, equivalent to 0. Now the proof here is that what we are going to prove is that this expectation of particular estimate, like here we are taking slope coefficient, is equal to true population coefficient or population parameter. This we have to prove. So if we have this particular term in the right hand side, so definitely from the basic mathematics we know that if we want to prove left hand side equal to the right hand side, and here the right hand side in form of beta 1, so we need this particular value, and this value is only in the yi function. Now this is the value of yi, right? The population equation, yi equal to the intercept plus slope coefficient multiplied by independent variable plus residual term. And only here we have this population parameter. So intentionally, deliberately, we going to put this here because we have to prove that expectation of this beta 1 hat is equal to beta 1. So beta 1 is only in the equation of population equation of yi, and that's why we need here yi. So that's also a reason that we are going to use it, and this term is already disappeared, so we left with the yi. So we are putting value of yi. Now we know that from the population regression function that this is the value of population regression function by independent variable. You can use notations beta 1 hat, beta 2 hat, the choice is yours. So don't get confused with this small beta and beta 2. That's only the notational change from one book to another. Now we open this particular bracket. I hope after the class you try to sort out these derivations, because this is only you only learn when you do it by your own. It's not that I am explaining you getting all the points, because there are 10-15 points in one single derivation. So it's not possible to remember that or keep cram that, and there is no need to cram that. It's just to understand this process, that yes, this is proved, and how it is proved, that's only the derivation part is. But when we are going to use the regression model, the important part is that whether this property is fulfilled or not. It's not that you all the time remember this derivation part. No one is going to ask you this. Now this is the equation. What we have to prove is that expectation of beta 1 hat equal to beta 1. So here the three terms are there, so it means we only need a single term. So let's prove other things equal to 0 or 1. So what it means that we need this particular value, so we have to prove that other values are 0 and this particular term is 1. Then only we can prove that this particular value is equal to expected value of this particular beta 1 hat. So let's start with the first term, summation ki. Just puts its value xi upon summation xi square. Open the bracket, this okay. Put the values of small xi, that is x minus x mean, and we know that this is equivalent to 0, summation of x minus x mean. So this is 0. So this summation ki is 0. So this term is disappeared. Now let's come to the next part, summation ki xi. Now puts its values. Small xi is equal to xi into x mean. Now just open the bracket and take a summation. Its first term summation xi square. Then in second case, x mean is constant, so it's outside the summation, and then summation xi. Now this denominator term, just solve this denominator term. This is x minus x mean square, so a square plus b square minus 2ab. Now solve this particular term, summation xi square, 2 mean, and summation x is opening the bracket because mean is constant, so outside the summation. And with the constant, summation is that multiplying the n. Now one another trick here, that in place of one of the means, just put x summation x upon n, that is equal to mean. So if we multiply this term x mean with the summation xi n, that's equal to mean, then it's a x mean square. This is the only trick we are using here. Now cancel these n into n, and now you can see these terms are similar. So 2, it's 2 and it's a single term, so 1 will be cancelled out, so it's remaining with the summation x square minus mean summation x. That's what we have in the numerator. So this numerator will cancel out with this denominator term, and it's equivalent to 1. So here we have proved that it's 0. This particular term is equivalent to 1. So we will remain with beta 1 plus summation ki ui. So just put these values of ki here again, and the purpose is that we have to prove expected of beta 1 hat is equal to beta 1. So just take expectation on both the sides, and we know that expectation of constant is constant, so this term is going to be beta 1 only. Now we left with this second term. If we take expectation here, it's now x, we have said in the assumption that is fixed in the repeated sampling, so it's a constant weight, so that comes out of the bracket. Or if you're going with the Gujarati, there it's written that x is a non-stochastic term, means it's not a random term, it's a fixed in the repeated sampling. So that's the property of expectation, that if it's a constant term, constant will come out of the bracket, and expectation is only with the variable. So here again, now since we are saying that xi is a fixed in a repeated sampling, it's a constant term, so expectation is only with the residual term, which is varying from one individual to another individual, or one time period to another time period. So now from the assumption, we know that expectation of expected value of this residual term is equal to 0. That we also proved with the numerical properties, and we also have this assumption in the OLS. So now this term is again going to be a 0. So we only left with the expected beta 1, and we know from the property of expectation that expected value of constant is constant. So in the right side now we have only beta 1, and in the left side expected value of beta 1 hat, and that's the unbiased property we want to prove, that expected value of beta 2 hat, or if it's beta 1, then expected value of beta 1 hat equal to a beta 2 hat. So this is the unbiased property. It is second property of this Gauss-Markov theorem. linear and unbiased. Now, again, just in a brief, that here again we use this particular value because we know that in the yi only this beta 1 will appear, and that's why we opened this particular equation. This get disappeared. We left out with this. In the yi there is a beta 1 value, and other term we have given name ki. We solved it. First term is equal to 0. The second one is equal to 1. This term with the expectation, it proved that it is equal to 0. So we had proved that expected value beta 1 hat or beta 2 hat slope coefficient is equal to the population parameter. So that's a property of unbiased. Now same thing you have to do with the beta 1, because here it's about the slope coefficient. The same thing you have to prove for this another coefficient, that's about beta 0 hat or beta 1 hat, that's the intercept coefficient. So again you have to go with this particular process. Now here you have to put the value of yi, where you will find this beta 0, and again similarly you have to solve all these values, and you have to prove in the end that it is equivalent to beta 1. That derivation I'll give you in a just 2 or 3 minute video form just after solving that derivation. If you want, you can go through that, because the purpose here is only to give you this glimpse that what unbiased is mean, and how we prove it with the bivariate or matrix method. It's not that for all the individual sample estimates you have to prove it, because in practicality you only have one sample. It's just that theoretically you have to understand that you can use these estimates because on an average they are equal to the population parameter. Not individually, but at least their average value is equivalent to a population parameter. This is the unbiased property. So next we have minimum variance. Any doubt in linear and unbiased? Kagan is there, Yaman is there, and Sivasa. Any one of you? Any doubt in linear and unbiased? Although these you have to practice 1 or 2 times, then only you can understand this process of derivation. Okay. So the next part is minimum variance. Okay, before that, just give you this unbiased with the matrix method as well. In matrix method, now here it's not required that you do separate for beta 0, beta 1 hat, beta 2 hat, beta 3. No, you have a matrix of this beta matrix. So just by proving that this expected value of this beta matrix is equal to the beta matrix, that's the population parameter. So here in the derivational writing form, it's not required that you can solve individually for all the parameters. It's only for the matrix. So in the matrix, if you remember from the derivation, that value of beta is beta matrix actually. Let me give you again. This we proved with the matrix method, right? Is what value of beta matrix is equal to. So now we have to prove that it's unbiased. How you can prove that? Again, you have to put the value. Now here we have a y, right? This is a y matrix. And y matrix is x matrix multiplied by beta matrix plus residual term. Don't get confused with this u and e. Actually, this epsilon, it's from the William Green. They use this notation for array term. And in all other books, generally you will find this u for the residual term. Now again you have, because we want to prove is that expected of this beta matrix that is from the sample is equivalent to the population beta matrix. So here we have to put the value of y. Same we did in the bivariate, right? We are putting the value of y. Now y matrix is equal to x matrix multiply beta matrix plus residual matrix that we did in the matrix method. Now just multiply this. Now here in this particular beta, because we know that A inverse into A is equal to identity matrix. This is now identity matrix, so it's only remain with the beta matrix. Other terms get converted into a identity matrix. And what identity matrix is that main diagonal terms are 1 and other terms are 0. So if you multiply any matrix with that matrix, the value will remain same. That will not change. Then we have to multiply this whole term with the residual as well. So that will remain here. Now take expectation on both the sides. The expectation with constant is constant that we proved in the last, and that's the property of expected values. And then expectation with the other terms. So now we know from this property that x is fixed in the repeated samplings. So this residual, this expected value is only going to be for this particular residual term. And we knew that from the property that expected value of the residual is equal to 0. So this whole term is 0 and we only left with beta matrix, that's the population's parameters. So it is proved that expected value of sample estimates is equivalent to population parameter. So in matrix, it's not required one by one. Means for whole matrix, if you can prove that, that's sufficient. That expected value of sample estimates is equal to the population parameter. Any doubt here? Just two tricks are here. One, the identity matrix property we are using here, and other thing is that since this x is fixed in the repeated sampling, it's a constant term, so it's come out of the expectation, and expectation will remain only with the residual term. And this is the assumption we have that expected value of residual is 0. So this term will get converted to 0 and we will only remain with the beta matrix of the population parameters. And that's equivalent to expected value of sample estimates. And that's unbiased property we have. So this is with the matrix method, which here is not required one by one. For the whole matrix, you can prove that unbiasedness. Then the next property we have minimum variance. Now, again, this is very crucial property that now here you have to keep this thing in mind that for the minimum variance case, the case is like, if I have a graph, let's see. Yeah. Let's suppose you have a two different estimates from two different methods. One is from the OLS method and another from any other method. Let's use any other method. The minimum variance property means is that the variance of your sample estimates which you have calculated from the OLS method is minimum as compared to variance of other sample estimates that you have calculated from the any other method than the OLS. So it's saying that the variation among your sample estimates with the OLS method is less as compared to the variation among other sample estimates from any other method. So That's the means important property they have. We have that here the variation is less among the sample estimates. So that's what it means, that this unbiased, which we have proved earlier, that this average value of expected sample estimates is equivalent to the population parameter. But it's not that always we have equal, right? Means individually it's not possible. It's for the average of all the sample estimates. But let's suppose if there is so much variation here, then we can't means have some positive implication to use it. But if we have proved that this is a these estimates have a small variance as compared to any other method, so it means we can rely on these estimates, and we have this, that okay, although they are going to vary from the population parameter, but they are just nearby because we have this property of minimum variance. So that's the relevance of this particular property, minimum variance. So to prove minimum variance, that I'll take that class maybe tomorrow, although I'm for the whole day tomorrow I have to travel from one place to another, because these days I'm out of home. I'm in Himachal due to some work. Last 2 days spent with one university, but it's not conclusive about the accreditation part for this course. So let's see, maybe in the future. So this minimum variance derivation I'll take in the next class, but before that we need variance, because last time we only did a derivation of estimates, sample estimates, not their variance. So this is a next part in the derivation, that to prove this property, first we need a variance value of these estimates. So first just take a derivation of this variance, that how we find this variance for all these estimates. So first we are going to do it with the matrix and bivariate method. Then after that we will do this minimum variance. Because last time the derivation only we did up to this particular part, right? Estimates, it's estimates only, not the variance part. So next we have to get derivation for the variance. So first just start with slope coefficient. Okay, so it's proved that it's unbiased. So now we need a variance to prove minimum variance. So how we calculate this value of variance? Just for a second, I have. Okay, first now you have to understand the formula of variance. In the simple descriptive stat, if you remember, the variance formula is summation x minus x mu and divide by n. That's the variance formula we have in the simple by descriptive stats. But if it's in a form of expected, means when we have a probability term, then it's in the form of expectation. So generally the formula of variance is expected, means if let's suppose it's you're taking in form of an individual variable like x variable. So x minus its average, that's mu, its square, and that expectation of that value, that's the variance of that particular variable. So similarly, in place of x, what we have here, we have a beta, right? This beta 1 hat. First, we are going to find its value, means what's the value of variance of beta 1 hat. So the formula is expected. Now, beta 1 hat, like it's if it's x, then it's x value minus. Now, in this particular property, see, it's a mu. Mu is the average, right? Average of the x. So in probability term, what will be the average? Average is expected of that particular variable. Now here we have expected of beta 1 hat. If we take its square and take its expected value, it's a variance of beta 1 hat. This is the formula of variance in form of probability. These properties you can see in the end of Gujarati textbook, or if these small properties you want to go with these, just go with the any 2 or 3 minutes videos from the Khan Academy in the YouTube. There you will find this all the properties: variance, covariance, expected values, then summation properties. All these properties are there. So to get a better idea, if you are doing it first time, with practice you will get these points. Now this is the formula for variance, right? Now next we have proved here that in the last unbiased property that this expected value of beta 1 hat is equal to the beta 1. It's actually beta 1 hat is here I took it from the Kotsyanin notation, so it's for the slope coefficient, means if it's our beta 2 hat if you are doing with the Gujarati. Now this is the formula, but now we have to get this formula, that for how this formula we get. Now beta 1 hat is equal to that we did in the unbiased property, summation ki yi, and ki is equal to xi upon summation xi square. So variance of beta 1 hat is equal to variance of summation ki yi. Now here you might have two different methods, means I'm going to give you example from both the methods. Yeah, for both the methods. This one is from the Kotsyanis and this one is from the Gujarati. Means both will give you the same value of the variance of slope coefficient, but their methods are different. So I'm just sharing with you this both the methods so that any time you are doing it, it won't get confused that these values are different. Actually, they used two different approaches. For simplicity, first just go by the Gujarati approach because it might be easy for you. In last unbiased equation, if you remember this equation, this one, right, or this particular equation, beta 1 hat minus beta 1 is equal to summation ki ui. Why this value I'm talking here? Now see the variance formula. It is beta 2 hat minus expected beta hat square, and we proved that this is unbiased estimator, so it's equal to beta 2. So we need value of this particular, right? Beta 2 hat minus beta 2 or this beta 1 hat minus beta. So this value in the unbiased had proved that this was in the our last equations. So Here you can get this value that beta 1 hat minus beta 1 is equal to summation ki ui. Just put this value here. Beta 2 hat minus beta 2 is equal to summation ki ui. Don't get confused again. This small beta 1. This small beta 1 is equal to beta 2 hat. So just put this value here, right, from this particular equation. Now just get this value in detail, that what it means for this particular term. This is the summation of ki ui and square of this term. So what it means if we break it down, summation is that individual multiplication, right? Means the individual summation of all the values. So you have these two terms. What it means that ki square u1 square k2 square u2 square means their individual multiplications. Then the like this is formula like it a plus b square, that a square plus b square plus 2ab, right? And then a plus b plus c whole square, then it's a square plus b square plus c square, then 2ab and 2c, right? In that particular form, we just open this. Here you have few terms with the ki ui square, and then other terms with 2ab, 2ba, 2ca in that particular form. Now this trick, this value is opened in such a way because there is a trick we have to use here, that deliberately we are using this method here, if you call it the Gujarati method, because from the assumption we know that expected value of ui with the uj, that's the no autocorrelation assumption we took, that one residual term is not correlated with the another residual term, that's expected value is 0, that we can use here. Because if you can break it down this particular term in this particular form, then you will remain with two parts. One is the square part, another is the 2k and the u parts. And this k, we took this as an assumption that x is fixed in the repeated sampling, so it comes out of the expected value. So expected value only remain with the expected ui uj, means all these terms, and all these terms will be 0 because of the assumption. So we will only left with this particular terms. And in these particular terms, let me give you this. Okay, let me give you solve this for you, because you might not getting this idea. I hope there is no doubt that this is equivalent to expected summation ki and ui. So here you have to break this particular term, that what it means. It means is that expected k1 u1 k2 plus kn into un and its square, right? Means summation of all these terms and its square. This description I only got from the notes from one of teacher in the masters. Actually, he did this course from the New Zealand, and his derivations are really useful. So, Mixer, I think these days he is in Punjab Fatehgarh Sahib in World University. I don't know the full name of that university, but his derivations are really means the steps the way he explained, quite useful for those who do it first time. So after this particular break, now you have to take. I don't know why suddenly these dogs start barking and what they want from us. So what it means? K1 square U1 with the like in the formula of A plus B whole square. Then K2 U2 square and so on. Then Kn square Un square. And like if we have this A plus B whole square, it is equal to A squared plus B squared plus 2AB, right? So in this form, now this all the terms are A square, B square till the n. Then we have 2AB. So that start with the 2 K1, K2, U1, UT, 2AB, then K1, K3, U1, U3, and so on till the end 2Kn minus 1, Kn, and Un minus 1 and Un. Why n minus 1? Because we know that if we have a 2, then we have a single 2AB term. If you have a 3, then you have a 2 2AB terms. So that's always one less compared to other terms. So it's still n minus 1. So if we take open this expectation here for this particular term, the expectation is with first just let write this particular term in summation ki square ui square, that is for all these terms, and plus 2 summation I equal to 1 till n minus 1 and summation j equal to I plus 1 and n ki, kj, and ui and uj. Just try to understand the process. It's not that you have to cram it out. Now, if we open this bracket and take ki is the from the xi and that's fixed in the repeated sampling. So expectation is only with the ui square. And here this all the constant term is outside. So this expectation is only with un and uj. And this is by assumption of not or correlation is equal to 0. So this whole term is get converted into a 0. And we only remain with the summation ki square into expectation of ui square. Any doubt so far in this part? This term did this to prove you that how this is equivalent to this term. This term now only left with this particular term. And here this is again an assumption that expected value of ui square is equal to a variance constant. That's also you can say that homoscedasticity assumption we have that expected value of residuals in the square of this, the variance of this residual is constant. So this is again an assumption. So we can put this value expected ui square is equal to constant variance. So what will be remain in the formula then? Constant term summation ki square, put value of ki, that's the formula for variance of beta 2. Sigma square divided by summation xi square. Sorry, here I missed a square part in the end, but it's a square. So the formula for this variance of beta 2 is beta 2 hat is equal to this particular term. This term is sigma square by assumption, constant term, and this term ki square. Put a value of this ki, that is xi, and summation xi square. This is the value of ki, right? And this is the square of this term. So one of the square is get cancelled it out. So we have a value 1 upon summation xi square. This is xi square. So this is the formula for variance of beta 2 hat. Sigma square upon summation xi square. This last part. And if I go it by for Chinese method, that's quite easy. That they won't use this particular value. In place of that, they directly use this variance of beta 1 hat is equal to, because beta 1 hat is equal to summation ki yi. So just put a value of ki yi, and since ki is a constant term in the repeated sampling, it's outside the variance, and variance is only with the yi, and variance of yi is equal to this sigma square of residual terms, variance of residual terms. That actually in this Portianis, they proved it that variance of y is equal to this particular term. So they just put this particular value here, and the same now they have this variance beta 1 hat or beta 2 hat slope coefficient is equal to sigma square 1 upon summation xi square. So but for that this particular derivation is required, and in this particular case again this is required that this particular derivation we have to prove. Means in both the way we have to prove this, that expected of ui square is equal to sigma square, or we have to prove that variance of y is equal to sigma u square. So means then it means if we go by this particular method of Gujarati, then we need this particular derivation to prove it, because we are using this as assumption. And if we go by Chinese method, then we need this particular property that y variance of yi is equal to sigma square. So for just let's see this Chinese proves that why this variance, and that's also give you us this distribution of y, that we say is it a normal distribution. So this is the distribution of dependent variable. Here they have proved that yes, this variance of yi is equal to this particular constant residual variance, and this property they are using there to get a value of variance of slope coefficient. So this proof is quite easy, that it's just that variance of y is like y minus expected value of y. Sorry, here square will also come here, and this yi minus expected yi, that is our residual term, right? In samples we have y minus y hat, that's our residual term, and its square, I missed here the square term with the square, and this is equivalent to this particular. So again means if you go by this particular method, again you have to prove this property. So in both the methods, even if you go by this Gujarati, we need this derivation, that why this is equivalent. But theoretically it means that expected value of this residual term, or the variance of the residual term, is equivalent to this constant variance. And with that they have proved that variance of beta 1 hat is equal to sigma square divided by summation xi square. So this derivation is required to variance part. So those of you who are doing for the derivation purpose, This derivation is very important. Otherwise, it's not possible that we can say that variance of beta 2 hat is equal to sigma square divided by summation xi square. So either you can go with the Gujarati method or by this Court Chinese method. This proof you have to prove. But this is the value of variance of beta 2 hat. Similarly, we have to get a value of beta 1 hat, the intercept coefficient. So that I'll only put the beta 1 hat derivations recorded in format so that you can solve that out. If any doubt, you can ask me later on. But beta 2 I shared here with you, and okay, so already 12:47, so I have some work to do. Okay, so in next class, I'll prove this particular now the third property, unbiased. That's we are only left with that finds minimum variance. For that, first we need a variance value. So now we know the variance value, but still keep this in mind that here one assumption or property we are using, and that proof is required. So that proof I'll give you in the end of all these derivations. So that's also important that we say that expected value of ui square or the variance of ui square residual terms is equal to some constant variance equivalent to the population variance. And that with that only we can say that variance of beta 2 hat is equal to this. So either way you can use this Gujarati method or this Court Chinese method. That derivation is required. Means in this Court Chinese method also they had used this property here that expected y of this particular residual square term is equal to this particular constant. So this derivation in both the way we have to work with that. So just keep in mind that so far today, because then it will be too much for the one day. First we did the linearity, then unbiased, but I only explained it today with the slope coefficient or with the intercept coefficient. I'll give you that derivation too. And for the minimum variance, first we need the variance formulas because these formulas first we need, then only we can prove is it a minimum or not. So today I only give you the value of variance of slope coefficient, but still keep in mind one of this assumption that expected ui square is equal to the sigma square. That proof we need to get this minimum variance. So that proof we will do in the end because that's important. So I don't just put that derivation. I'll want to explain that derivation. And maybe any one of you just watching these videos for the exam purpose for master and all, they might ask these derivations in the final exam. So they need it in detail. And only if it's about the applied part, then it's not that you have to cram this derivation, but just try to understand that these properties are proved for the OLS estimates. And that's the reason that we prefer OLS estimates. These properties have this significance, but that's only when assumptions will fulfill. And that's the reason we use OLS estimates with these properties. So at least you have to get in this idea that what these properties are. Blue property means if you are using these estimates, so definitely you have need to this confidence that okay, you are using it and it's they have these properties unbiased, minimum variance, linear. So it means they are better to use these estimates, but that's only with the assumptions. So I hope this is enough for today. So in the next class, first we'll prove this minimum variance for this slope coefficient, and then for the same, we will do it with the matrix method as well. And after that, that will be the last part of these derivations because only for properties only these three proofs are required: linear, unbiased, and minimum variance. Then we will only left with this one part that expected value of this residual square is equal to the sigma square. That we will do in the end because that indirectly we are using in these derivations. And then we will jump to other methods. And what about the goodness of fit of the model? Then what about the hypothesis testing of the individual coefficients or the overall model? So that's we have to do after these derivations. So thank you so much. So I'll inform you about the next class. Might be tomorrow in the late evening or in the morning Friday. But in that case, I also take class on Saturday and Sunday as well. I'll try to take on Saturday and Sunday as well.